Today we're going to start looking at some of the other organic compounds. The first few lessons we just focused in on hydrocarbons and different types of hydrocarbons, but now we're going to branch out and see what happens when we start adding other atoms to chains of carbons and hydrogens. So we're going to look at haloalkanes, alcohols, aldehydes, ketones, and carboxylic acids. We're going to look at their structures, we're going to look at their naming rules, so how to name and draw them, and also try and tie in some of their properties as well, with what types of intermolecular forces you can see in those molecules. So, first thing we're going to do is walk through all of the rules and their structures, and then we'll get practice with some naming and drawing. First group are haloalkanes. They're also called alkyl halides. If you're reading different sources, sometimes they're called alkyl halides. The alkyl part comes from an alkane chain, and the halide comes from halogen. Or you have haloalkane, halo for halogen, and alkane for the carbon chain. But you could have halogens attached to alkenes, alkynes, and other places. But the thing to remember is you have a halogen attached. So, when we describe the properties of the molecules as we go through them today, we have this column here called functional group. So for a haloalkane, our functional group is going to be this X. X for us is any of those halogens, fluorine, chlorine, bromine, or iodine. When you see the notation R being used in any of these shorthand forms, what it's referring to is the rest of the hydrocarbon chain. That just means it could be 1 carbon long, it could be 10 carbons long. It's just attached to that main chain somewhere. Now, in terms of naming rules, these ones are very easy. Halogens you treat as side chains. So the side chains we've seen so far, like a methyl or ethyl or propyl and so on, these ones have a different name. They don't use the YL ending, they have an O on the end. So to call them by their names, we have these prefixes we add on: fluoro, chloro, bromo, or iodo. So pretty straightforward. They work just like a branch. They need a number. You need to put them alphabetically. All of those rules from before still apply. Next group up, let's take a look at alcohols. The class of family is called alcohol because of the presence of a specific functional group. The functional group is called a hydroxyl group. An oxygen attached to a hydrogen, which is attached to the rest of a hydrocarbon chain, that's called a hydroxyl group. If you see that attached on a carbon chain, it tells you you have an alcohol. How do you name an alcohol? It's very easy. You're going to use a position number to say where the OH or hydroxyl group is attached, just like you might have done with an alkene or an alkyne. But the ending of the name changes. Instead of ANE, if it's an alkane, we get rid of the E and add on OL. Let's take a look at our next group. Our next group is called an aldehyde. An aldehyde has a functional group called a formal group. Now the formal group is a carbon bonded to an oxygen, but it has a double bond, and that carbon has to have a bond to one other hydrogen. What that means is this will always be on the end of a chain. And for us, if it's at the end of a chain, with the examples we'll see, it's always going to take the number 1 position when we count how long the chain is. This R here is just to signal it's attached to the rest of the molecules. So it could be another carbon. This could even be a hydrogen if you were dealing with a 1 carbon aldehyde. So this functional group is called formal. When you're naming your longest chain, like we said, the formal group carbon, this one here, has to be number 1. So your base chain name and number starts at the formal group, which is this one here. The ending also changes in this case. Instead of A-N-E, drop the E and put A-L on the end for aldehyde, al. A closely related group, it's called a ketone. A ketone's a little bit different. You'll notice that the carbon has a double bond to oxygen, but this time that carbon has to be bonded to two other carbons. This one has to be a carbon chain, and this one has to be a carbon chain. They can be the same length or different lengths, but this carbon has to be bonded to two other carbons. The notation here with the dash beside it is just to signal they could be different or they could be the same in terms of length. But this group here has to be joined, two bonds to carbon and then the double bond to oxygen. This functional group is called a carbonyl group, or sometimes called carbonyl, depending on how you're pronouncing it. Just like other groups, when you're numbering your base chain, this one you want to give this group the lowest possible when numbering. So just like we did for double bonds or triple bonds, we try and give them the lowest number. Same thing with carbonyl group. Try and give that the lowest number possible. Ending is very easy. Instead of A-N-E, drop the E and put on O-N-E for ketone. The last group that we'll be covering today is the carboxylic acid. Carboxylic acid, its functional group is a combination of two that we've seen. And here this is a line diagram, but this could be a carbon right in there. So this carbon has a double bond to oxygen on one side, a single bond to another oxygen, which has a hydrogen attached, and then it's bonded to the rest of the carbon chain over here. We know this group we called a carbonyl group, and this group here we call the hydroxyl group. So taking carbonyl and hydroxyl together, this group is called carboxyl. The functional group is called carboxyl. This one, because it has to have this bonding structure, it's also always going to be on the end of a chain. And this one, we always give it position number 1 when we count our longest chain. So the base chain here, we start at that carboxyl carbon and we count 1, 2, 3, and so on. Like you've seen with the others, this one also has a suffix change. So we take away the E from A-N-E, we add on O-I-C, oic, and then we put the word acid because this is an acid. Before we go on and actually start doing some naming and drawing, the other thing we should start thinking about are some properties. Hopefully you're filling out your properties table as part of your work, but where do you want to think about properties? So properties like melting point, boiling point, state, hardness, all of those things come from the presence of intermolecular forces. So with intermolecular forces, there's different things you can see might be showing up because of these functional groups. Carbon-carbon bonds and carbon-hydrogen bonds are pretty boring. They're pretty much nonpolar. So now by adding in these functional groups, we're adding in more character to the molecule and changing the types of intermolecular forces. So for example, if you're adding in a halogen, you're adding in opportunities where there's going to be dipoles present in the molecule. So you could end up with dipole-dipole forces, or if fluorine's involved, you could even have hydrogen bonding. So this adds some polar character to the molecule. What happens if you're dealing with the hydroxyl group in an alcohol? Oxygen bonded to hydrogen, we know that's going to create a dipole, and that's going to give us an example of hydrogen bonding. Remember, with intermolecular forces, hydrogen bonding is the strongest one. So this one's going to create stronger attractions between those molecules, which could lead to higher melting and boiling points and so on. When we look at aldehydes and ketones, they're going to have similar types of intermolecular forces. They'll both have dipoles that form around that carbon and oxygen that's there. So there is some dipole-dipole forces that happen in both of these. So around that functional group, it adds again a little bit of polarity, which can change the melting or boiling point. Out of all three, the carboxylic acid has the most for bonding in terms of intermolecular forces. It's got a nice dipole here, and then there's two dipoles that point towards that oxygen. Here you get a dipole-dipole force, or you could accept a hydrogen bond. Down here you're definitely getting hydrogen bonding. So basically, when you're looking and reading more about these molecules, think back to those types of intermolecular forces that you learned more about, and they'll help to explain some of the properties that you see. So now what we're going to do is start practicing some naming and then some drawing of these molecules. So we're going to walk through a few examples together, and then we'll let you try out a few. So we're going to try and identify the type of organic molecule we have and give a correct name for it. So let's start with this one over here. When we're trying to identify what molecule we have, the best thing to do is look for something that's not a carbon and not a hydrogen, because that'll tell you what group it belongs to. So when I look, the main chain here is all carbons and hydrogens, but then I can see, wait a minute, I've got some halogens attached. So here, this is going to tell me I have a haloalkane. So then I need to think, okay, if I have a haloalkane, how am I going to name it? The halogens are treated like branches, and the branches end in O with their name. Just like other branches and molecules, I have to find my longest chain, and I need to make sure my branches have the lowest numbers. Nothing's changed here. So when I look at this one, I count 1, 2, 3, 4, 5, 6, 7. When I look at where my branches are, they're on 2, 3, and 4. So I know numbering left to right is going to give me lower numbers than going the opposite way because the branch is closest to this end. There's no other groups present here, so I can start to name it. I have chlorine and fluorine. Just like before, you have to follow alphabetical rules. Chlorine goes first. So I'm going to put 3 chloro. And I have 2 fluorines, so just like when you have multiple groups, the same rules apply. 2 and 4 difluoro. And it's 7 carbons long, so this is heptane. So 3-chloro, 2,4-difluoroheptane. All right, now let's take a look at the next example. So here it is over here. I'm looking for something that's different than carbons and hydrogens. So right away I can see, okay, I've got an oxygen double bonded to carbon, but I also have an OH group attached to that carbon. Because I have that there, I have to think, well, what type of group do I have? This here is my carboxyl group, which means I've got a carboxylic acid. So now that I know I have a carboxylic acid, I need to count. This carbon automatically becomes carbon 1 in the chain, and I have to find my longest chain, which I'll see if I go this way. So 1, 2, 3, 4, 5, 6. That means on number 2, I have a branch. So what if you have a branch? Still works the same way. Branch goes out front. Branch is on number 2. This is an ethyl group. Then my longest chain is 6 carbons long. So hex. If it was just hexane, it would be ANE. But now I'm not going to put the E in, and I'm going to replace it with OIC, and then the word acid. So this one's called 2-ethyl hexanoic acid. All right, let's try a couple more. Here are the next two. So first, again, let's find the functional groups, and we'll do it for both of these together. So we're looking for something that's not carbon and hydrogen. Over here, we've got a carbon bonded to oxygen double bond, and over here, we've got the same thing. Are they the same type of family or not? We have to think, where do we see this carbon double bonded to oxygen? One place you see it is with a ketone, and one place you see it is with an aldehyde. Positioning is different. So, how do I know which one is which? Look where the functional group is and what's attached. This carbon here has a hydrogen attached to it, and then there's more carbons over here. Whereas this carbon has a carbon-carbon bond here and a carbon-carbon bond here. This group is on the end. This group is somewhere in the middle of a chain. So just by looking at the position of the functional group, you can tell which one's an aldehyde or ketone. This one over here is an aldehyde because this is your formal group on the end. Here, because the carbon double bonded to oxygen's in the middle, this is a ketone. So you have the carbonyl group present. Once you've sort of thought about that, then you have to think about the naming rules. With an aldehyde, this is always number 1, and we count our longest chain starting number 1 there. So this is carbon 1, this is carbon 2, and this is carbon 3. No branches, this is a small molecule, so I go and start to name. 3 carbons is prop. Normally we put propane, A-N-E. I'm going to keep the A-N, but for an aldehyde I put A-L. So this is called propanol. Propanol. Over here with the ketone, I have to do the same thing. I need to number my longest chain, but most important is giving this group the lowest number. Then worry about the branches after that. So if I'm going to do that, I'm going to number it left to right. That gives my carbonyl group position number 2. That means I've also got 2 branches on carbon number 4. That's okay. They work exactly the same way as we just saw. So what do? 2 groups on number 4. I'm going to put the 4 twice. Then I put dimethyl because they're both the same. Then I start with my longest chain hex. Normally A-N-E. I'm going to keep the A-N, saying I have all single bonds between the carbon. But then I have to say where the carbonyl group is. It's on number 2. So I need to put a dash, a 2 and a dash, and then O-N-E for ketone. Let's take a look at a few more examples. Here we've got a couple of different structures. Again, the rule when you're learning, what I always suggest you to do, find something that's not a carbon and hydrogen. So clearly we've got an oxygen here and a hydrogen. And here, lots of carbons and hydrogens except for here. So looking at these 2 molecules, could you tell what family they belong to? When you see the OH group on its own like this, that's the hydroxyl group. And if you see hydroxyl, you have to think alcohol. This is an alcohol molecule, and this is an alcohol molecule. Okay, now what if it's in a ring structure like this? Not to worry. How you would number it, you're going to follow the same rules as before, but the hydroxyl group gets the priority. It means it gets a lower number than any just regular carbon branches. So I'm going to number this carbon number 1, the one that's right here, And then I have to count around my ring structure, but I need to make sure my branch gets the next lowest number. So here I'm going to go 1, 2, 3, 4, 5, 6. I have a branch on number 2, so I'm going to start with that. Number 2, I have a 2-carbon branch, so this is ethyl. Then I have my cyclic structure, so I put cyclo. It's a 6-carbon ring, so I need hex. ANE for all single bonds, but I drop the E and I'm going to put on OL. You could put a 1 in there or just leave OL on the end. So 2-ethyl cyclohexanol. Let's try this alcohol over here. We want to number it so that this group has the lowest possible, which means carbon 2. But I've also got a branch on here, so I need to put that first. 2 for the branch. It's a methyl group. Then I have a 3-carbon chain, so prop. I keep AN because all single bonds. But then I have my OL ending, and since it's on number 2, I need to indicate that with my position number. So 2-methyl propanol. One more to go. So over here, this is something a little different, just to give you a taste for what can happen when you start mixing some other groups. When you're dealing with aromatic compounds and you start attaching functional groups to them, you'll find that they fall into a slightly different naming pattern. And if you're curious, there's a chart posted up in the aromatic section of our content so you can see derivatives of aromatic compounds. But this gives you an idea at least of one. Here we've got our aromatic ring here. That's our benzene ring. It's hard to attach certain functional groups right in the benzene ring or right to the benzene ring depending on what's there. Here we can see we've got a carbon, double bond to oxygen, and a single bond to OH over here. This is your carboxyl group, which means you've got a carboxylic acid. When it's attached to benzene, the carbon has to be separated out because if you put the carbon that has the carboxyl group in the chain, it would break the bonding rules. This carbon has 1, 2, 3 bonds around it. If you try and stick it in that ring with benzene, it's going to have 6 bonds around it, which is going to be a problem. So this one, its common name, is called benzoic acid. You can also sometimes see it called benzenoic, but a lot of the aromatic compounds have some different derivatives. So you generally won't be evaluated on those derivatives at this level, but if you're reading and see them, this is just one example to give you a taste of what's going on. So now that we've walked through a bunch of structures and the names, let's try drawing a few and give you some practice. So here we're going to draw some molecules. You can draw them whichever way you like, whatever structure is more comfortable. But the key thing is look for features in the molecule that tell you what's going on. Here we've got an OL ending. Any guesses what group it could belong to? After looking at your list, this is telling you you have an alcohol. And then you have to think, okay, what's unique about an alcohol? It has an OH group, the hydroxyl group. So when I go and draw this, I can start thinking. I've got prop, which is 3 carbons, AN for all single bonds between my carbons, and then I've got my hydroxyl group on carbon 2. So when I put it together, I've got carbon 1. On carbon number 2, I have my hydroxyl group. I need a hydrogen there. And then this is my 3rd carbon. 1, 2, 3. Let's try another example, and then I'll give you a few minutes to try the others so you can pause the video. We've got 3-methyl butanol. So this here is our branch. But means I have 4 carbons. Again, AN still means all single bonds. Between the carbons. But what I'm looking at here is the AL ending to tell me what group it belongs to. AL ending means you have an aldehyde. So what's an aldehyde unique about it? You've got the formal group. Formal group is that carbon with a bond to hydrogen and a double bond to oxygen. You don't see numbers with this one because it's number 1. So let's start to do this. With these ones, I'm going to put my formal group on first. This is carbon 1. Then I've got carbon 2, so I need CH2. But on carbon number 3, I have a methyl branch, so I'm going to put that in. We're not at the end of the chain yet, so I need one more hydrogen, and then CH3 for 4 carbons long. 1, 2, 3, 4. So there are 4 more on your notes. What I'd like you to try and do is see if you can pause the video and try drawing these 4, and then I'll walk you through how to draw them after this. So pause the video, and then we'll walk through the answers. All right, let's start taking a look. 1-chloro-3-fluorocyclopentane. So I see the chloro and the fluoro. That tells me haloalkane. And I've also got some extra part added in here. It's a cyclic structure. So if I'm drawing, I'm going to start with my longest chain. Cyclopent, ring structure with 5 carbons. So I know I need my pentagon shape. Then I'm going to need to add a chlorine and a fluorine. Doesn't matter which one you start as number 1. Let's say we do this one. 1 is chlorine, and if I wanted to count clockwise, 1, 2, 3, then I would put my fluorine in there. Let's take a look at the next example. I take a look at my name. I've got a branch on number 2. My longest chain prop is 3 carbons, but on the end here I see oic acid. This means I have a carboxylic acid. A carboxylic acid has to have a carboxyl group. So when I draw this one, I'm going to draw my carboxyl group. You could stick it on any end of the molecule. I put it on number 1 here. Then I need 2 more carbons. This is carbon 2, and then I've got carbon 3. On carbon 2, I know I need a methyl group, so CH3. That means I need an extra hydrogen in here. And nothing is attached on my 3rd carbon, so I put my hydrogens in. If you haven't tried the last 2, now again, before we take up the answers, would be a good time to pause and try them out. With this one, I see right away my ending here says ONE. This is telling me I have a ketone. Ketone has that carbonyl group. It's saying my carbonyl group is on number 3. How long is my longest chain? My longest chain is 5 carbons, and AN means I have all single bonds. So I'm going to start to draw it. Carbon 1, carbon 2, here's carbon 3. I put in my carbonyl group, 1, 2, 3. My 4th bond is on this side, no hydrogens attached to it. CH2 and CH3. So 1, 2, 3, 4, 5. Let's do our last example. But, 4 carbons, all single bonds. Then I see this ending, diol. Di still means 2, So what I really want to look at is the very end, OL. OL means alcohol. But I've got two alcohol groups, two hydroxyl groups, one at 2 and one at 3. So CH3, carbon number 2, I've got hydroxyl group, carbon number 3, here's another hydroxyl group, and here's carbon 4. And there's my butane 2,3-diol. So hopefully going through those examples of drawing gets you to start seeing some patterns with the naming, seeing where the endings change, and how you can identify which group they belong to and draw them properly. One last question to finish our lesson off, and this is going to start tying in some of our properties. Which of the following compounds would have the highest boiling point? And try and explain your answer. Anytime you have a question that has to do with properties, you want to think about intermolecular forces. So what I would do first is try and draw the structure of any molecules you're asked, because that'll give you a visual cue as to what groups are there and what forces you might have. So try first, pause the video, draw these 3 structures, and then we'll take a look at the forces together. Okay, we've got butanol. Butanol is an alcohol that's 4 carbons long. My hydroxyl group will be on carbon 1. You can point it up or down, it doesn't matter. Okay, this is butanol. Next, let's draw butane. 4 carbon alkane. Then our last one, we just saw this. Let's make that a different color. There we go. So this one is also an alcohol. All right. So once you've got that done, the first thing you're going to do is look at the length of the carbon chain. This carbon chain has 4 carbons. This one is also 4 carbons, and this one here is also 4 carbons. So we're dealing with the same length chain. Why does this matter? If you're comparing something that's very different in size, like 4 versus 12 or 10 even, what's going to happen is the London dispersion forces are going to take over. Okay, so you have a lot more atoms, you have a lot more electrons, and those London dispersion forces are going to be present in quite a strong amount. So if you're comparing boiling points or melting points, generally you'll have structures that should be around the same length. But if they're not, you can still see that. Just know that larger molecules tend to have higher melting points and higher boiling points because they have more dispersion forces. So when we look at all of these 3, the easiest one to start off with is butane. There's only carbon atoms and only hydrogen atoms. So in this particular molecule, the only type of dispersion force you have are London dispersion. Why London dispersion? This is pretty much a non-polar molecule. Carbon-carbon bonds are non-polar, carbon-hydrogen bonds pretty much non-polar. If we start looking at the 2 alcohols, will you have London dispersion? Sure. There'll be London dispersion for both of these. But because you have the hydroxyl group present in both, you're going to have some hydrogen bonding. With butanol, you have 1 opportunity for hydrogen bonding. But with the butane 2,3-diol, you have 2 opportunities for hydrogen bonding. Remember, when you start adding in functional groups, it changes the properties. Hydroxyl group is a polar group. This adds some polarity. And the polarity, again, is due to dipole-dipole force. Just a special type with hydrogen bonding. The more dipoles you have, though, the stronger the intermolecular force will be. So, this has no dipoles, butane at all. It only has London dispersion. This one has one strong dipole area with hydrogen bonding around the hydroxyl group. But butane 2,3-diol has two. Because there's two places for hydrogen bonding to occur, it has more dipoles. And with more dipoles, it's going to be more polar. And the more polar means you have higher melting and boiling point. So, after going through this analysis to actually answer the question, we would need to explain the following things. We would say here, our boiling point is affected by the strength of intermolecular forces. When we look at intermolecular forces, it's obvious butane has the weakest. Since it has the weakest, it will have the lowest boiling point of the three. Then we have to justify which one's higher. The butane 2,3-diol has the strongest. Therefore, it's going to have the highest boiling point of the three. So hopefully that example gave you an idea of how to actually explain some of the differences you might see in properties of similar sized organic molecules. Look at their functional groups, look at what types of forces can be present. The more forces or the more polar they are means they're going to have higher melting and boiling points. It can also affect their state or solubility in different substances and so on. So the key with these are, make sure you get lots of practice, practice the functional group names, practice the family names, and practice drawing as well.